All right, so what we're going to do here is work through some of the intuition that will link kinematics in angular kinematics and linear kinematics, which is really important, and work on some of the visual intuition that is so critical here. So as we get started, let's go ahead and draw a circle, and let's say this is a wheel, and the wheel is going from right to left here. So let's say this wheel spins at 5 radians, or let's say the wheel just spins a total of 5 radians, and so theta is 5 radians here as it goes from right to left. And remember with that, and let's say the radius is 0.6 meters. So remember that the radian is the angle that a circle makes here if the arc length matches the radius length. So the radius length here should be 0.6, and then the arc length here would also be 0.6 meters. Okay, so it goes around one arc length, 2, 3, and then 4, and then 5. So the question is, how far? That's how far angularly. And remember, all the way around is 6.28, which is 2 pi radians, is a full 360 degrees. So that's 6 radians, and then just a little bit more, 0.28, would be a full circle. In this case, we only go 5. And so each of those lengths, right? If this is 0.6 meters here, the length here is 0.6 meters, the arc length. So we can add them up. We have, 0.6 here, 0.6 here, 0.6 here, 0.6 here, 0.6 here. And so 1, 2, 3, 4, 5. So if we multiply those, we take the arc length, or the radius rather, and which is the arc length, and we multiply that by 5, and we get the linear length. So that would be 3 meters. So our relationship is distance is equal to taking the radius times the angle in radians, and that will tell us how far linearly. What's interesting about this as well is, if it travels around 3 meters, that means that's linearly, how far the wheel has gone around, and that's how far over the ground it's gone. And that's going to be really important as we move forward here. All right, so let's take a look at the second example. Here's a wheel that has an angular speed of 4.3 radians per second. So with our intuition here, here's our first radian, where the arc length matches the length of the radius. Second, or 2 radians, 3 radians, 4, and then a little bit more, 0.3 more, right? So in 1 second, that's how much it rotates around. Now, let's say the radius is 0.8 meters, and we want to find out, how many meters per second does it go? Well, we can approach this the same way. So we have, the radius here is 0.8 meters. That arc length there is 0.8, then 0.8, and then 0.8, and then 0.8. Now a little bit more. Now this is in radians. This is 0.3. So that's 30% of, 0.8. So that would be 0.24 more linearly right here. So that arc length with only 0.3 radians is going to be 0.24 meters, multiplying that amount of radians times that. So our total length will be 0.8 plus 0.8 plus 0.8 plus 0.8 plus 0.24, which is a length of 3.4 meters. So that is how long this is around as it goes around, and we get a total of 3.44 meters. So the linear speed will be 3.4 meters per second. And that's how far, we covered here with the arc length, and then we covered that with that. So our relationship then, we take our angular speed, which is 4.3 radians per second, and we multiply that by the radius. So we take the radius times the angular speed, and then we get the linear speed, and that is v. And so hopefully that's clear now that you can see that length, and you can see that time. So it works very similarly to the last one there. All right, so in this example, the initial angular speed is 10 radians per second. And let's say that the alpha for this, the angular acceleration, is -2 radians per second squared. And so this is going to be slowing down, and let's say it slows down to a stop, and this is not to scale here. I'll put a little ziggly line here that there's a gap here, so eventually it comes to rest. And the question is, how far angularly has it gone? So this would be good practice. Go ahead and pause the clip real quick and calculate the angular displacement, theta, for this, and then we'll go from there. So go ahead and pause the clip, and when you're ready to check, you can hit play to continue. All right, so we know omega final squared equals omega initial squared plus 2 alpha theta. And the final angular speed is 0, the initial angular speed is 10, and the angular acceleration is -2 radians per second squared. And we can solve for theta, and we should get 25 radians as the displacement as it goes. And yeah, so we've got that. And so if the radius is 2 meters, how far linearly has it gone? And so you should be able to do that as well. So go ahead and pause the clip and give that a try. And when you're ready to check, you can hit play to continue. All right, so you remember we take the radius times the number of radians, the angular displacement. And so this will go 50 meters. Now, if we want to relate this to what's going on linearly, it turns out that if we take the radius times the angular acceleration, we get linear acceleration, just like we did with, d, the distance equals r times theta, and v equals r times omega. Similarly here, if we take the radius times the angular acceleration, we can get the linear acceleration. So if we do that, we take 2 meters times the angular acceleration, -2 radians per second squared, and we get -4 meters per second squared. Now, if we also take the initial angular speed, which is 10 radians per second, we can multiply that by the radius, and we get 20 meters per second. So we can actually treat this now. We know that this wheel itself, as it goes, is going 20 meters per second, this wheel here. And so that's the linear speed. It's not the angular, it's the linear speed as it goes from left to right here is 20 meters per second squared. And then the angular acceleration is 4 meters per second squared. That's how much it's slowing down. So and then it's going to come to rest. So we can use the kinematic equation, final velocity equals initial velocity plus 2as displacement, and we can figure out the displacement. The final velocity is 0, the initial velocity is 20, and we have the acceleration, and we get the same thing. And this wheel itself right here is going to go a full 50 meters because it's going 20 meters per second. The acceleration is -4 meters per second squared, and as it goes, it's going to come to a stop. And so the interchange between these is direct there. So to summarize, the first thing we looked at was we can find the distance by taking the radius and multiplying by the angular displacement, the radians of displacement here. We can find the linear speed by multiplying the radius times the angular speed. And then finally, we can get the angular acceleration, or linear acceleration, by multiplying the radius times the angular acceleration. And so in all these cases here, you just take the radius and multiply it by the corresponding variable here, which is, for distance, it's omega, which is or theta rather, the radians of displacement. Here we multiply the radius times the angular speed to get linear speed, and then finally we take the radius times the angular acceleration, we can get the linear acceleration.